Hey guys, so this will talk about the calculation of pH. Our next unit is on acids and bases, and performing this calculation is going to be critical. It's going to come up with a lot of questions, and it's how we quantify how acidic or basic a solution is. And so I want to make sure that you guys all know what you need to do in order to calculate this. I'm not sure if you've had this in your first year chemistry course. Sometimes they get to it, sometimes not so much, and sometimes the accelerator gets to it and the regular doesn't. So again, I just want to make sure everyone's on the same page here. And to start off with, we're going to talk about what's called the ionization constant of water. So water is a very cool substance for many reasons, but as far as acids and bases go, what water does is it can react with itself, and it reacts with itself by, looking at this through the Bronsted-Lowry method. There's a proton that gets transferred from one water to another, and in doing that, it's going to form hydronium ions, and then it's also going to form hydroxide. So this is equilibrium, and at 25 degrees Celsius, this equilibrium constant, and we give this a special name. It's an equilibrium constant. We call this Kw. Okay, it's the ionization constant of water. It's right up there. And at 25 degrees Celsius, this has a value of 1 times 10 to the minus 14th. Okay, so it's very, very small, which means that, for a glass of water, this equilibrium lies way far to the left. It's mainly just water, right? But there's a little bit of it that does react with itself and forms the H3O plus and the hydroxide. And when we express this equilibrium constant, we have liquids over here, so those don't go into our equilibrium constant expression, but this Kw is going to be H3O plus times OH minus. And that, again, at 25 degrees Celsius, will be 1 times 10 to the minus 14th. And 25 degrees Celsius is our at room temperature, so mainly we'll use this. And for a neutral solution, so you just have water hanging out and there's nothing added to it. For a neutral solution of water, each of these have to be equal to each other. So H3O plus will have to equal the concentration of hydroxide. And for this, it's going to be 1 times 10 to the minus 7th molar. So in pure water, a neutral solution of water at 25 degrees Celsius, all these caveats, this concentration is going to be 1 times 10 to the minus 7th. I do want to mention, though, that if you're not at 25 degrees Celsius, then this will have a slightly different value. And because this has a slightly different value, this condition holds true. These two will have to be equal to each other. But what that means is that these will no longer necessarily be 1 times 10 to the minus 7th. It might be a little bit different, which, fun fact, as we'll see very soon, means that the pH of pure water at some temperature other than 25 degrees Celsius may not be 7. It may be something else. Okay, so let's talk a little bit about pH and pOH and how we define it. So from this, I'm going to go back a slide here. From this, you can see a neutral solution, this concentration of hydronium, and this is what we're going to be basing pH off of in this Bronsted-Lowry view, is H3O plus. And also the concentration of hydroxide are very low, and we're chemists. We want to spend our time doing reactions rather than writing everything out. So we're going to find a shorthand way to quantify this concentration. And we've done that by pH. And so pH is a logarithmic scale. And it's defined as negative log of the concentration of H3O plus, or in the Arrhenius view, this could also be H plus, right? And so that's the definition of pH, and it's logarithmic scale. So when we have this hydronium ion concentration, if it is equal to 1 times 10 to the minus 7th, then what we would say, the pH is negative log of that, okay? And so it'd be essentially, since this is log base 10, it'll be log of this is negative 7, take the negative of that, so this will be a pH of 7. And in order to get a pH of, say, 6, right, a drop of 1 pH means that our new hydronium ion concentration needs to be 1 times 10 to the minus 6. And so there's a 10-fold increase in going from one pH value to another. It's an increase or decrease. Also, as pH goes down, the hydronium ion concentration goes up. Okay, so you're going to have to keep that straight too. Lower pHs mean higher hydronium ion concentrations. But changing a pH by 1 means a change of 10 times in the concentration. And just as we can calculate pH value, we can also calculate a pOH value. And that's going to be defined very similarly. So it's going to be negative log hydroxide ion concentration. Okay, so we got this one right here. And then we got this one right here. Okay? All right, so at this point, we have essentially 4 different things we may want to calculate. We have H3O plus concentration, we have hydroxide ion concentration, we have pH, and we have pOH. And you guys need to be able to convert between them. So I'm not going to say I did make it, but I'm not saying this is super original. But I call this the square of pHness. And so what you can do is you can make this little square. And so we have H3O plus concentration, maybe pH, and pOH over here, and hydroxide ion concentration over here. And we can convert between any of these by going around the square. And so if I want to go between H3O plus and pH, I'll use negative log of H3O plus. Okay. Or, I could take 10 raised to the power. So we'll work on going from pH to H2O plus concentration. If I'm going to go between these two, I'll use the Kw expression. Okay, so Kw is H3O plus times the concentration of OH minus. And again, for our purposes, really, Kw will almost always be 1 times to the minus 14th. I just wanted to mention it to you guys. It doesn't have to be, and some cool stuff results. To go between these two, we have negative log of hydroxide concentration. And to go between these two, and I should explain this, but I can drive this in class for you. But if we are at 25 degrees and the Kw is 1 times 10 to the minus 14th, we can say pH plus pOH is equal to 14. Okay, and so we'll be using that. So this square here, and make sure you get this in your notes, allows you to go between any of these two things. So say I have H3O plus concentration and I want hydroxide, I'll use this conversion factor. If I want to know what the pOH is, and I have this, then I can go to figure out pH, then to pOH, or I can figure out what this is, then go to pOH. So I can go around the square this way. So you go between any of these. Okay. So maybe I should show you that. I'm feeling guilty here. So H3O plus concentration would be 10 to the negative pH value, and hydroxide ion concentration would be 10 to the negative pOH value. Okay, now I can sleep tonight. So that's how you'll go back and forth between these two. Either going this way, use the log. Going the other way, you take 10 raised to the negative pH or pOH as appropriate. So that's the information you guys need. We'll practice doing this in class. If you have any questions, let me know.